Yay, finally. This is kind of discouraging when we think about these matters at hand, like self-driving cars. If this takes up this much time, then we have no hope. Anyway, welcome to this this first presentation. And first of all, I want to let you know that I am definitely not an expert on this topic. I'm a data scientist. I've been working at Futurice for 2 years. I'm a career changer, so I'm not like incredibly experienced throughout millennia in data science even. However, I was thinking that we might approach, I think this is the first time we're having presentations in one of these meetups, I believe, yeah. So I was thinking that maybe you should approach this as, and you know, like people have these things called book clubs or something. So when everyone is pretty clueless and ignorant and helpless, and then they decide that, you know, someone reads a book or an article and then, you know, sums it up for the others. And then people take turns. So this is my attempt. I took an article called Key Ingredients of Self-Driving Cars, and I read it through and I pretty much condensed what was there. And then I put some, like, I looked for some pictures to go on with the article. And after me, there's going to be another presenter who probably has much more experience on the subject. However, we'll start out with this one. So, well, also apologies for the Audi plug. I was trying to find an anonymous car, and then I even tried to Photoshop it, but that looked even worse. So now you'll just have to live with it. So, let's move on. So, autonomous car systems is the topic. And if you think of an automated driving system, then their main point is to, well, basically enable these cars to operate in real-world environments without intervention by human drivers. Now, it doesn't have to be completely automated. It's very helpful if it's just like, you know, partially automated, as we all know. And these systems can be divided into two parts, the hardware part and the software part. And you may have seen these before, but this is kind of like an official, I don't even remember what SAE stands for, but these are defined as the levels of driving automation. So there, when you look at this table, there's HD stands for human driver, and then there's some other acronyms at the bottom. But at level 0, when you have no automation, the human driver is responsible for everything. And then incrementally, the system starts taking over. And I believe that these higher levels are like way ahead in the future, but this is kind of a hopeful table that has been set up. Now, everything starts with the sensors. And some of you probably have been tinkering with a car, so you know a lot about these sensors. But here's just an overview of what would go into an actual, like not like mini size, but an actual autonomous vehicle. First of all, there's cameras. And well, this is not from a real, like human size car. This is from our Markku. So there's not much use of this yet. But this is a tracking camera. So a tracking camera basically takes care of reporting where the car is, where it is. It's important to track it through time. And then there's the possibility of taking a stereo camera and images that are slightly different, and then with algorithms constructing a 3D model of the environment using that camera without a LiDAR. And here's the one that we have here from Markku, and we have great plans for this. And then there's also just, well, there was this company called Wayve, as in W-A-Y-V-E, who developed maybe a year ago this car that they were training with reinforcement learning. So a human driver would drive it, and then, you know, in 20 minutes or so, it would learn from the corrective maneuvers of the human driver. And I believe they were just using one monocular camera. So no stereo vision, just a single camera. So maybe you don't necessarily need all of that stuff. Well, it's a good idea to have many of those cameras, but still, they don't have to be super fancy, even for real cars. Yeah, so as I said. And this also is Elon Musk's favorite tactic, because as we will come to later in this presentation, he absolutely hates LiDARs. And there it is, LiDAR. So for light detection and ranging, laser pulses that are being reflected back, and then from the reflections you can deduce the 3D structure around you. And this is the kind of stuff that comes out of them. It would be incredibly nice to be in that place during this time of year. So They are short wavelength, obviously. They have a wider field of view, and the problem with them is that they kind of have a short range, at least the affordable LiDARs. And this is Elon Musk's pet peeve. He thinks that they're almost evil, as he has stated. I don't remember how long ago this was, but he has stated that people using LiDAR will be doomed, and that they will realize that they've made a huge mistake. And the reasoning is that, well, it's an expensive piece of hardware, and if, again, you have something that can break, and it's useless in his opinion. And there's actually research to prove this also, although the argument in the previous slide wasn't like super convincing. But however, and this was from an article published, I think, sometime around like maybe a couple months ago. So in Cornell University, they were actually, bending towards Musk's approach in this, that maybe you shouldn't be using this expensive piece of hardware. However, it's super cool, so I don't think people will be giving up on LiDARs yet. Then there's radar, which is of course in use already with longer wavelength. And this is very good for cases where detection distance is important, so you need a long distance. But the exact size and shape of the objects are not like recognized as well because the wavelength is much longer. And then there's ultrasonic transducers. And here's an example of a Tesla model with the radar. And well, there's just one camera, apparently just one, okay. And then there's 12 ultrasonic sensors. So these kinds of things usually form up the sensor palette. Then there's GPS. Sorry, what?
Flight laser sensors.
Sorry, I still could.
Time of flight.
Okay.
Time of flight laser sensor.
Okay, thank you.
It's a brand new, relatively new.
Ooh, do you want to tell a bit more about it?
Yeah, it's there's a sensor from ST Microelectronics. The exact sensor is VL53L1X,
Okay.
and it basically measures the distance with the time of flight of the laser. So it hits the laser, it reflects back, and then it just measures the time.
Okay, cool. And it apparently works like better.
I think it's the same principle as the LiDAR. It's
Okay.
just a single units.
Okay.
So instead of using ultrasonic sensors, you could use ultrasound sensors. You could use the
Okay.
TOF sensors.
Okay, cool. TOF sensors, everyone.
Yeah, just an addition.
Imagine that slide there.
Thanks.
Okay. And well then, of course, there's GPS, but the problem is, as people know, that the signals can be very weak and they can be easily blocked, and especially when you have high buildings and these urban canyons, it's a problem. So you need these IMUs and or wheel encoders as backup for them. But in all cases, you will never find an ultimate winner sensor, so that you just have like one sensor. You will always have different types of sensors and fuse data from them, and that's a good idea, and there's redundancy and everything. Then there's this far infrared. Now, I may have fallen for an advertisement for far infrared, but I was checking out this article, and it seems that it would nicely complement this, these other sensors, and it's been used, but not like everywhere. So here's an example. So in scenarios when there's not very much light, it could be a very good addition, and especially this image is kind of convincing. And then without the far infrared, when we look at these three that we've talked about now, like the camera, the radar, and the LiDAR, and think about the areas. These are like diagrams that demonstrate how well this type of sensor is doing in whatever kind of environment. So that a camera is good at picking up contrast and resolution, and a radar is not so good. Then apparently, since there are some sectors missing, at least the people who came up with this this article state that the far infrared would be a very good idea to add to this palette. But these are the kinds of things that you have to consider when thinking about the set of sensors that you will be putting on the car. Then there's the hardware controllers. So you have a motor, you have a brake, you have a throttle, a gear shifter, and a parking brake. our cars, or these little cars that people have been tinkering with, obviously don't have these necessarily, but for actual cars you will need them. And about software, and this was something that I had not heard anything about, but apparently there are these different software architectures that go by these names. So in whatever way you want to divide up these tasks, there's many ways of approaching it. And there are these things called the Grand Challenge or the Urban Challenge. And for example, this first architecture type was used in the Grand Challenge, and the second and third ones for the Urban Challenge. So you can look at those lists, how they've like divided them: 4 modules, 5 modules, 3 modules, always differently. And for this paper, what comes next is referring to this kind of structure. So, I mean, they're referring to this as their proposed architecture for this system, but I assume this could be generalized. So it starts out with the sensors, and then there's a perception module, and there's a localization and mapping module, and then there's prediction, then there's planning, and at the same time, there's control to go with it. And then there are the hardware controllers. And then localization and mapping has to involve communications with other vehicles. So now for very, very short introductions of these modules. And as I said, this is going to be an overview, basically just introducing these names. Hopefully there's something you haven't heard before. Even if there is, this is, repetition is the mother of something. I don't know what it is in English. Anyway, the perception module. So this is the module that is responsible for object detection and tracking. So you're looking for like free space and vehicles and pedestrians and signs. And then there's the aspect of having to reconstruct a 3D world using structure from motion or stereo vision or LiDAR. And the state-of-the-art perception technologies at the moment are divided in 2 categories. There's computer vision-based, and then there's machine learning-based. So with computer vision, you take these geometry models and you use optimization approaches. And with machine learning methods, obviously, you use data. And CNNs, mostly, convolutional neural networks. And you've tinkered with those, certainly, if you've tinkered with a car. Then there's the localization and mapping module. So its tasks are to estimate the location and to build and continuously update the 3D world map. And there's this method, or I guess you can call it a method, of the SLAM, simultaneous localization and mapping, which comes in 2 types. There's filter-based, and then there's optimization-based. And again, I don't really know much about this. If someone is an expert on this, please speak up now before I speak. Okay, enough silence. So how I understand this is that the first one, the filter-based, is about incrementally taking in the sensor data and going with it and not really like looking back, but the other one is looking back at the previous poses, and there's a difference. And yes, definitely look into this. This keeps coming up everywhere. This SLAM, and it's the key to everything. Although it was invented in the 80s already, I believe that they're only now making good use of it because there's so much more computational power available. But, well, in essence, when something is moving around, it constantly has to know where it is, and it has to update its map accordingly, as we do, but we are born with this skill. Then there's the prediction module, which analyzes the motion patterns of others, a big issue. And of course, it gets easier when everyone starts using autonomous vehicles, because then, there's less observation to be done. You can perhaps trust the information that you're getting from those other vehicles. A host of other problems from there as well, of course. But the prediction module predicts future car trajectories, its own and those of the others, enables the autonomous car to make appropriate navigation decisions. Again, there's morals and ethics involved with this, but I'm just conveniently skipping that part. So, 2 ways to make these predictions for now: the model-based and the data-driven based. kind of like analogous to the differences in having a model or having just data. And then there was this mention of people trying stuff out with inverse reinforcement learning. Now we're going to hear about reinforcement learning in the next presentation, and perhaps you can bombard the presenter with questions related to inverse reinforcement learning, if you wish, but I can guarantee nothing because I've only heard about it like a while ago. Then there's the planning module. So its task is to determine the possible safe navigation routes based on the information that it has received from the previous modules. So you have to do three things. You have to plan the path, and you have to choose the maneuver, and here you obey the traffic rules. You can, of course, remove this need, so everything gets easier, but then you go to jail. And then there's the trajectory that has to be calculated, and I think this is the part where you actually think about things like the comfort of the passengers, because you could, of course, take a car from point A to point B in a horrendous way for the passengers, but you might want to accommodate them. Then there's the control module, which is all about throttle, brake, and steer. So you have an ideal state, what you want to have, and then you have the observed state, and you try to minimize the error function between those. And then, why do I have this strange highlight here? There are open source datasets. How many of you have made use of these? Some kind of open source datasets. Have you just like collected data from your own little car? Mostly. Okay. Well, there are some available, and I don't have the URLs here, but I think we'll be posting this presentation somewhere, right? Yeah, so I will add them in due course. So definitely check them out. Again, this weird highlight. And then about this industry leader thing. I was looking at these I guess these are considered the leaders at the moment, but then when I was looking at the accident rates, they were so strange. Like, in this article, it said that something like General Motors had, what was it, like 2 accidents per 200 kilometers or so, but then Tesla had like 1 accident per 3 million miles. I don't know if there's something wrong with those metrics, but I have to check them out. But obviously, well, how do you measure the successfulness of these? There's so many things to consider, like the safety thing is probably first, but there's many dimensions against which you can measure them, of course. But and yes, the universities are also like keeping up nicely. But yeah, there are challenges, many challenges. But according to this paper, at least, the main challenges were related to the perception module for now. So there's the issue of poor weather, and you have probably run into this when training your cars. Poor illumination, so there's darkness, there's contrast. Like, for example, you go to a tunnel. That is something that many of these systems have a very hard time handling. I mean, even like the pro systems. You have bright sunlight, and then you go into a tunnel, or you come out of the tunnel. So sunlight, sun contrast, and there's reflections and shadow. And then I believe that snow and all kinds of strange forms of, snow, slush, and, these things that Eskimos have like a million names for, they're probably not like at the center of investigations in places like warm places where a lot of these things are being researched. So I believe that there's additional challenges related to snow and cold climates and, well, black ice, of course. What is wrong with my writing? I'm sorry, I was in a hurry. And my network connection also failed on me, so I'm double sorry. But then there's, the complex urban environments, and the methods are still a bit intensive. Actually, now thinking about the Elon Musk argument, I mean, wouldn't the point of using lidars being that you kind of get to sidestep a lot of the computation? I don't know, I'll have to read the paper. But then there's, apparently there are some issues with this simultaneous localization and mapping thing, so it's unstable in the long term. And anytime when you're trying to detect the position of a particle, you're probably using some kind of method to like accumulate measurements from the past, and then when it goes on for a longer time, then it starts going out of whack. So I assume that it's related to that. And then there's the grand problem of fusing all this sensor data for a better semantic 3D world and doing it fast, doing it cheap. And then a whole new can of worms, and I'll be ending this presentation here. This huge can of worms is, of course, the acceptance of autonomous driving and autonomous cars. But as we have seen with like elevators, for example, I do not pine for an elevator operator here, and that was something that people had a problem with. They didn't trust an elevator that didn't have a human there. I would actually be very distrustful of an elevator with a human like driving it, and there's many other examples. So people will be coming around, but when and will we live to see it? I don't know. So with this, I'll leave you with the image of, like, we had this beautiful Audi picture in the beginning, and this is where we are now. Not to be discouraging or anything, but yeah, go Markku. Thank you. Do you have a statement to make? Do you want to use me for it? Oh, you have another mic. Thank you.
No statements, but thank you, Inka. And next, Natalia.
Okay, I think I have quite an ambitious title, right? But I was thinking like how to call it and how to make it more general. And I came up with this title. So sorry if it's too general. I come from Tampere University. Like former part is Tampere Technical University, and I'm doing postdoctoral research there. I started a year ago working more on robot learning, and before that, I come from signal processing department, so not from RoboLab or mobile lab, but from signal processing, and before that I was doing signal processing for some underwater robots and some computer vision. My PhD was about computer vision, but in more traditional sense, so I did it 6 years ago before the rise of the neural networks. But nowadays, as you know, there are like neural networks everywhere. And a year ago, I started my Academia of Finland project about robot learning. And then we have several more people doing their PhD, masters. So I'm now going to tell about robot learning approaches and about recent trends that I like and that you might want maybe to use in your systems or in future work. And then I will tell like my favorite project from all that we are doing, and maybe like more from the practical side, so that you would also like have a look at how it works. Like previous speaker, I think we, how was that word? Like we contemplate or like each other, because now we will maybe go more like for learning and see like some examples in practice how that could be done. And I prepared a slide where I kind of formulate this racing problem as the reinforcement learning and say what are the components there that if someone might want to try. And also I have some good hint like how I would approach it. And actually we have a bachelor student approaching it that way. So maybe he will at some point join this event, but we have different cars, you will also see. So let's kind of go to the topic. There are robots. Robots are very different. They are nowadays, like I think when I was doing my PhD 6 years ago, I completed, but started it like 10 years ago. And I think at that time, this learning were mostly like a lot concentrated on this vision side. For example, for computer vision, where appeared this ImageNet data set, and there was a lot of like work done on that. But robot learning was done maybe with more traditional methods like optimal control, and those two areas were not so much intersecting. Whereas now you see the conferences on robot learning, on robotics, conferences on those computer vision pattern recognition, and people might be the same presenting everywhere, and they realized that maybe like with all those methods for machine learning, they should go to robotics to make really the active systems. Like this is more fun, more usable, and maybe like handy to have. And robots can be like very different. There are like racing cars or just cars driving, self-driving cars in the streets, and there are maybe assisting robots, kids and elderly people, robots in the industry, robots in the warehouses that are moving the loads, or of course those robots which are automated for assembly lines. I don't show them here. And even like those, wow, still, even like those soft robots, for example, they also appear nowadays like artificial muscles. This is like a completely different world, but the world of robots is nowadays like enormous. And then, of course, we all know that there are those like supervised learning approaches and unsupervised learning approaches. They are traditional and they're used in the computer vision and or deep learning as well. Sort of, you know, that when there is data set labeled and you want to predict like some class, that's supervised learning. Unsupervised learning when you want to discover some underlying structure in the data. But then they are kind of good approaches, and then you might think like what is then the difference here, that what is lacking for the robots? Like if you just train a data set which, for example, even like recognizes all the people or recognizes all the buildings, if you have that computational power, then still that's not enough like for an active system, because it will make mistakes, and mistakes lead to bigger mistakes, and then like the system crashes, and with some system is too expensive to crash, like the cars. So then there appeared this whole paradigm of reinforcement learning, which is the learning where the agent takes an active part in it. So you have, where is my mouse? Okay. Here the difference is that this approach, sort of like as the reinforcement learning, it was formulated maybe like 50s, 60s. Before that, there are like optimal theory, game theory, all kind of these things, which then were sort of like joined together, and from there became this nice reinforcement learning area of research. So there is an agent. Agent acts in the environment. Environment here, he observes the environment, of course, then he acts, and then he or she, this agent takes an action that it thinks is the best, and then gets a reward. And this agent, of course, has some goal. Someone told the agent what is the goal. And then the agent tries to optimize its behavior. And then I listed here some like hints maybe for myself. So there you can see that there are problems with that, okay, it will take a lot of time from the agent like to perform in this environment from scratch, for example. Then who will actually formulate the goal, who will formulate the reward, like if you start thinking like, okay, how should I implement that? And then also like, what is the model behind that? Like, what are you trying to optimize? And then I go also fast through this sort of trends nowadays. So I don't go deeper in the details about like the theory, because maybe you can check it by yourself and maybe I can later talk about that. But I think those like several works that I mentioned now, and then you can check out, they are actually covering quite important topics which are now in the reinforcement learning, and that could be utilized then by you further. For example, it finds to be very handy to train in the simulator, like the previous talk was saying that, but I think we cannot. It's very, very important to train in the simulator, and I would definitely in your place like try to do it, because you save time and you save like resources, and then of course like how do you transfer from the simulator to the real world is another question. And in this work, like from 2019 in May, they said that they can train in the simulator similar system, and then they can use the trials from the real world with like similar robot to sort of like modify the simulator, which would then have features similar to the real life. Then there is an approach called end-to-end learning. This is also one of the ways like to approach it, like when you have only the sensory data, like no matter what, like a lot, maybe high dimensional, maybe RGB images, and then you just try like directly to match them to the actions. So you don't want to think like this in that structure, like okay, like the planner, the perception unit. You want somehow to build a pipeline which would handle like from the beginning to end. This is handy but challenging, but then some people attempted to do that. Then there is a very recent Nature paper, which I actually didn't read so much in depth, but it says that there are ways also to integrate memory into that. It also reduces the learning time and also usage of the resources. And then there are people who are creating a huge data sets for training, because they are doing it because if you consider a robotic arm, which some people have showed that, okay, this robotic arm can move this kind of cube like this on this table. And the problem is that what they demonstrated is only this exact robotic arm can move exact this green cube in this exact environment, so it doesn't generalize mostly. Yeah, so then they approached it like that maybe we create a huge data set, which would cover like many like possible circumstances in which this robotic arm can operate. Then there is like learning from demonstration. When you first demonstrate by the user or someone else like the correct behavior of the robot. For example, we were also attempting in the beginning in the bachelor thesis that to demonstrate the correct way of driving and then train some model. And then you can also think like maybe you can create some smart sampling of your previous experience while driving, utilize all the samples that you already collected from all the conditions. And also, as the previous speaker said, there is like model-based approaches. They are not only that you sort of utilize the model, like for example, describing the dynamics of the robot, but you can also learn the model that describes your environment. And I will also later a little bit show it if I have time. Okay, then I was thinking, okay, if we have this racing car problem, like what are the components there, how you go with a real solution? So first of all, you have to formulate your task. Like what is the thing that you are trying to optimize? Whether you want to follow the line as precisely as you want, or whether you want to drive as fast as you can, or you make a combined function that somehow is like a weighted sum of those two. Then you should decide, okay, this is your environment, what are the observations? Do you give only RGB image? Do you give some like LiDAR, or I don't know, like some distance to something? Or maybe you extract with your prior algorithm some features and then you like directly feed them. Then you have to decide about the method, of course. I just here briefly say that there are policy-based method, value-based method, so that or combined method, hierarchical, when you're first trying to reach one goal, and then, for example, first you might formulate it like keeping only close to the line, and when you learn to do that, your reward function becomes different, and then your new task is like to drive as fast as you can. And then you also will think like how to train all this thing, whether you use demonstrations or whether you use some virtual environment. And in our work, I don't know, have you seen this? Driving smoothly in 5 minutes. Did you see this? So it's like a very handy thing, I think. Well, wait a second. How to press it? So here there is a block. Wow. Okay, we don't need music here. I just want, the point here is that here the people written a blog post and they published paper and they presented in Python the virtual environment that you could use. We are at least using, because the track looks similarly. Only like the higher, like those features, like the sky may be different, but you can train there actually any of your agents there, even not necessarily the reinforcement learning. Although they already provide there some code, for example, for extracting variational autoencoder features. So the features that were like, these are the features which map, like, for example, from RGB space to some latent space that describes very well, for example, the image. So you could use this one. I think it's like a good idea. And then it uses this deep deterministic policy gradient, like the RL, one of the RL methods. So one could try that. And on top of that, we also think that it might be useful to get some prediction about the environment. And for that, for that, I know it comes everything very fast, but maybe it's anyway like stays in your mind something, and slides are available, so you can then just have a look. So the idea there is that can we model the environment somehow? And there was a paper which demonstrated that in the game planning they can like predict also like the future environment based on what you see and what action you take, and it helps you also to behave better there. So that's also one idea that can improve all these things. And there is like a link to the paper, and they have also code. But then, I don't know, do I have still time? Okay. Then I would like actually to show maybe something that we were working on. And it's not racing cars, no. We got in the Tampere University, we got this track, like thanks to Mikko, I don't know how this all happened, and thanks to Futurice. Yeah, but since we have this track now, we have also monster board cars. I don't know, for some reason, we already had monster board cars before we got to know that you have donkey cars, so we can still like think to change, but we have like several monster board cars, and we have like several students working on them. And so we, after we got this like in spring, we started like making up something with those. So maybe we will also appear here as a team one day. But all the summer, we were working on implementing some learning for a bigger machine, like this, like heavy-duty machine. So we were thinking, we are collaborating with automation department. So we come from signal processing, and the automation department, they build the control of this whole thing, like up there, here. And it has a bunch of sensors, also LiDARs and RGB stereo camera, Z camera. We are using Z camera. And we are using a bunch of pressure sensors here and there in the machine, for example, hydraulic driving pressure, and some pressure sensors in the actuator. And okay, we were like, okay, we would like to do reinforcement learning there. But of course, to train from scratch a big machine in the stochastic environment with a lot of like variation with the weather conditions and so on, we need some tricks there. So we either need the simulator or we need some kind of learning from demonstration. And we decided at that point, when we didn't have a simulator, nowadays we are going to get one. And we decided to record demonstration. It was like day before Juhannus, and we were thinking that, okay, we record maybe 100 demonstrations, and we did it like the whole day. So I also get skeptical when, because technical problems is 50% of our work, I think. Like you just start doing something, it's technical problems, so it's normal. It means that it's like progressing. Oh my God, it's like, I think there is some delay in video. But anyway, so that guy was like collecting out there the demonstrations. And also then again, there is this problem like who restarts the system, because the system has to go like forward, okay, performs the action. We want that it learns to scoop the whole bucket. But then someone has to reverse it to some certain state. And we also developed this method, like automatic going back, like caster people know the stuff. And yeah. Okay, so, and then I get skeptical when people say, okay, we have maybe like a professional driver who can in 2 hours collect for us like millions of demonstrations. That's not true. Yeah, when professional, like not so professional driver can collect maybe like in one day, maybe 100 or 200 demonstrations, so you have to be also modest in that. And this is example, like those are signals which we collected apart from the camera, and these are maybe some unsigned values, so sorry for them, like unsigned in. But anyway, like, as also like the previous speaker said, that there is like lots of data available, and one has to also to deal with those. Like here, like that, and this is the demonstration that we collected, so the machine sees it like that it's far away, then it drives up and then scoops, and the full scoop is like a good outcome. And then we also like recorded, for example, we had some idea like which pressure sensors might be good, or which not. For example, here is the boom angle and the bucket angle, but then here is this hydraulic driving pressure, and when it approaches the pile, so he has to drive in a certain way and like almost crashing into the pile. And then the hydraulic driving pressure grows, and then maybe it's the hint also to the algorithm, but we didn't specifically say that. These are some references our work is based on. So the idea behind there is that we will get the reward at the end of the action, and we will evaluate it visually. And sort of use the learning from demonstration. And the special thing about this work is that you are manipulating a granular material, like loose material, which is also presents for you some like extra stochasticities, like driving in some unknown environment. Also, the environment presents for you some like additional like variations, and this in here the same sort of, because you don't know how material will behave. You are modifying it, and it becomes complicated. We used like visual features which we trained. They were trained in some how Siamese network way, sort of that we want to distinguish between failure examples and the success examples, and we feed those kind of examples to those two networks, and we want to maximize the distance between the features of similar examples and minimize the distance between the features of the similar examples. And when they use random forest regression in order to match those demonstrations to the actions, and the random forest is actually a powerful, like nowadays there is a lot of research on this neural network and many people are using that, but if you are using the random forest, it gives you this possibility to select automatically the features. That's the first thing. And then also by this voting mechanism, among the trees, you might get some generality. So I would also try with the racing, something like this, some other approaches too. So I must disappoint you, we are working on the reinforcement learning, but we did the learning from demonstration. So we are on the way towards this learning from demonstration, but we needed some kind of also learning before. And we just show that, okay, it outperforms the state-of-the-art neural. Of course, we attempted the neural network controller. And the thing there is that when the person is demonstrating some actions, it sometimes shows them differently. So might take even a different route. So in the data space, it looks like multimodal data. And then neural networks sometimes learn average behavior, which is not so useful in those cases. So there is a reason why we also use the random forest. So, and we show that it works better than that. I don't know why it's something wrong with the video. Sorry, but it works smoothly. It doesn't look like.
How efficient is it right now?
Huh?
How efficient is it? Is this moving right now?
Yeah, we had some There is also this additional difficulty that when we recorded the demonstration and when we are testing, it always happens like a different daytime, a different, like sometimes evening, sometimes. So there is a big variation, and we might say that it succeeds in like 80%. I think it's quite good. Yeah.
So right now on the pile, when it's keep loading, the pile should advance, and then the machine should advance to engage the pile,
yeah.
right?
Yeah.
Does it do that automatically? Is that an account?
Oh, this is like, we don't know how it does. I mean, the algorithm does it.
Because the pile moves ahead, right?
Yeah.
So when the machine, the bucket engaged, sometimes has to go forward.
It's this. I think it's those hydraulic driving pressures that take care of that. Like there are, as I said, that there are like those pressure sensors in the machine which sort of help it to not only to see but like to understand. You are right that the pile is modified, right? Yeah. But still, I mean, when the pile begins, this hydraulic driving pressure, for instance, grows, and that gives some hint. And then when the bucket hits the pile, there is another pressure sensor that gets engaged. So, and those like are fed to the system. And then in the future, we want to robustify the reward. We want to robustify the features because there is lots of variation.
You do that through MATLAB? Like
No, Python. Yeah, MATLAB is like Simulink is responsible for the control, like of the whole machine, and we communicate with it with the Python script. Yeah.
Open source stuff?
I don't think so. Although this project is not sponsored by any like machinery companies yet, so if someone wants to collaborate, then. Should I throw it into you?
So yeah, just to clarify it a little bit, you guys have used supervised learning for this example,
Yeah,
right?
this is a supervised
And
learning.
you're planning on
Yeah, we would-
reinforcement learning in the future.
Yes.
So do you guys have some sort of like simulation that you're building or working on
Ye-
implementing, or is it going to be reinforcement learning in the
Yeah.
real world?
The thing is that actually in summer we were trying like really hard to make the work as this reinforcement learning. We spent lots of time like trying that, but we found out that the like to train from scratch we don't see any result and we cannot evaluate whether any method is working there. So now, just this week we were visiting Mevea and we will get simulators from them, and they are not exact copy of our machine, but they are anyway like some excavator there, and we can anyway train the things and see whether those methods that we intend to use, they anyhow like converge and produce any solution for similar tasks. Yeah, that definitely like.
So what you're saying is that like the reinforcement learning that you guys tried to do was in the real world, in your
Yes.
and that was not very successful, or it was very difficult to kind of
It couldn't
get results.
converge.
Yeah.
So I don't know. Yeah. It was doing something like we could say, but we were not so satisfied with the like reporting, for example, as a publication yet. But we are now working, and we created somehow a little simplified simulator, and when we get the sophisticated simulator, and then there is snow, which came even today, and we are hoping that we can show something fun, like with how it can change the environments. And this is very next important slide. These are us. Like this is Professor Joni Kämäräinen from signal processing, Riese Capcello from automation department, so he knows everything about those machines. And these are like, I don't know, you know, maybe people. So yeah, this is your track. Thank you again. We have those Monsterborgs there, and for those our student is developing. He couldn't attend today. I asked him that he could even like show something, but he couldn't attend. And then here is like how much time we spent in the yard in the summer. And then we have also like some little projects, for example, for navigation indoors. There are also like lots of databases open source like for navigation indoors if you're interested. But I would definitely look at that simulator of donkey car, right? Yeah. That's it. Thank you. It was cool.
I have a question. While you were doing reinforcement learning, how do you handle the balance of exploration and exploitation?
Yeah, there are different ways to do that. So you
Okay.
can do it almost like by random, or you can try to define some variable which over time by some measure gives less randomness.
Okay.
Or you can use this replay sampling of some replay buffer, so you also like see whether using your previous experience helps you to reduce the new exploration.
Mhm.
There are publications on that.
Okay. Yeah. Thank you.
Yeah. Oh yes, yes. 2 times we broke like, and it's quite crucial. Like you start doing it, and it didn't do anything like crazy. It just like hit very hard down. But then it occurs that in the design of the machine there was some kind of like maybe weak spot. Maybe nobody was supposed to do that, but it breaks some hose, and then it just leaks the hydraulic oil and needs to be. But now we know. Now there is some protection there. Okay, that's all. Nice to talk to you guys. Yeah, thank you.